Have you ever found yourself incredibly frustrated trying to explain the exact same rules to an AI agent every single day? You know the drill. You tell it your formatting preferences, you lay out all the constraints, you carefully walk it through how to connect to your database, and then, the very next morning, complete amnesia. It's forgotten literally everything, and you have to start the whole process over from scratch. Well, if that sounds familiar, you're definitely not alone. Today, we're diving into a really breakthrough explainer on a research paper from Apple that actually solves this exact problem of AI amnesia. The paper is called Shared Selective Persistent Memory for Agentic LLM Systems.
Okay, let's take a quick look at the agenda. We're going to cover the agentic memory problem, then look at the selective memory solution, exactly how it works, some real-world enterprise examples, the results and limits, and finally wrap up with the key takeaways.
All right, Section 1, the agentic memory problem.
So agentic LLMs are undeniably powerful, right? But they have this one massive, fatal flaw. They're completely stateless. Which begs the question, why do these supposedly smart AI agents have such terrible amnesia? In the real world, especially if we're talking about enterprise workflows, you don't just build a dashboard once. We build structurally similar things over and over again, like a weekly supply chain report. But starting from zero every single week, that wastes millions of tokens and just hours of human time. And that's because you're forced to respecify your domain constraints, your color preferences, and your really complex data schemas every single session.
Now, you might be wondering, well, why not just hit save on the chat history? It seems obvious, right? Actually, saving the full history just leads to massive information overload. Prior research has actually shown that feeding an LLM too much irrelevant context causes what's known as a lost-in-the-middle effect. And honestly, it gets worse. Feeding an AI its old, stale tool use traces or error logs actually biases and confuses the agent. It essentially anchors the AI to its old mistakes instead of letting it focus on the new task at hand.
And just to prove how bad saving the full history actually is, look at this metric right here, 71%. In the researchers' controlled tests, saving the full conversation history actually dropped the agent's task completion rate down to 71%. To put that in perspective, that's actually worse than having no memory at all, which sat at 79%. So counterintuitively, remembering everything is literally worse than remembering nothing.
Which brings us to Section 2, the selective memory solution. To fix this amnesia problem, we really need a memory architecture that's shared, selective, and persistent. A great way to think about this is using a baking analogy. So when you bake a cake over and over, you definitely want to save the structural rules, like the recipe, and you want to save your tool configurations, like your specific oven settings. But you absolutely want to throw away the messy, session-specific errors, right? Like dropping an egg on the floor or the dirty dishes piling up in the sink. The idea is simple. You keep the structure and you discard the mess.
So the researchers basically took that exact concept and mapped it directly onto AI architecture. They essentially decomposed all of this reusable knowledge into 4 really compact, stable categories. By breaking memory down into these 4 orthogonal buckets, the system only saves what's absolutely relevant. Let's break down exactly what goes into each of these 4 buckets right now.
Okay, first up we have task specifications, or MTask. You can think of these as your custom domain rules. These are the explicit, hard and fast instructions you give the AI, like always use green for over 95% attainment, or make sure to always include an executive summary card at the top. And the beauty is, once you establish these rules in one session, the memory system just locks them in for the future.
Second is data schemas, or MData. Now, instead of forcefully feeding the LLM massive, token-heavy raw CSV files, which is expensive and slow, the system pre-computes a really compact statistical summary. It looks at things like the column names, data types, and statistical distributions, and just saves that metadata. So this gives the AI exactly what it needs to write perfect data processing code without completely drowning in thousands of raw data tokens.
The third bucket is tool configurations, or MTools. This persists all those complex connections to your external environment, things like your SQL databases, REST APIs, or MCC servers. By saving this, you don't have to re-authenticate or re-explain how the company's internal database works every single session. The system just remembers the plugin.
And finally, we have output constraints, or M-output. This one is really a structural contract that's forced on the AI. It basically tells the agent, hey, when you write code, you must build programs that pull data from a live runtime injection point. It strictly forbids the AI from hard coding values. By separating the generated code from the live data, we unlock something incredibly powerful, which we'll look at in just a second.
But before we get there, we really have to look at what the AI intentionally forgets. Because what gets discarded is honestly just as important as what gets saved. By throwing away things like intermediate files, unapproved user changes, multi-turn reasoning traces, and error logs, we prevent the AI from getting anchored to those past mistakes. It basically starts every new session with a totally clean slate of logic, but armed with a full notebook of your rules.
Let's move on to Section 3, How Selective Memory Works.
So, because we force the AI to obey those strict output constraints, we get this incredible three-step workflow. Step 1. The system checks if your new weekly data has the same exact structure as last week's data. Step 2. It seamlessly swaps the underlying data. And Step 3. The artifact re-renders automatically. The researchers call this a zero-token data refresh. Basically, your entire weekly dashboard updates without spending a single LLM token. How cool is that?
All right, Section 4, Enterprise Real-World Examples.
Now, the researchers didn't just theorize about this, they actually built a collaborative workspace platform and tested it across 3 real-world enterprise scenarios using the Claude Opus 4 model. The first use case is the recurring refresh. Thanks to that zero-token update we just talked about, a weekly supply chain dashboard actually refreshed 14 times faster. Second is cross-team sharing. Imagine a director setting up a workspace with all those rules and templates and securely sharing it with a colleague who just plugs in their own local data. And third is iterative construction. The system uses a Git-backed versioning system, so if an entire team is building a complex report, they can actually undo mistakes and revert to previous states risk-free without having to reinvoke that expensive AI model.
Let's look at Section 5, Results, Tokens, and Limits.
And here is the massive win. 96%. Across the board, shared selective memory achieved an incredible 96% task completion rate. Remember those earlier numbers? This absolutely destroyed the no memory baseline of 79%, and it thoroughly crushed that full history baseline of 71%. It just proves that by curating the memory, the AI performs drastically better.
And this brilliantly illustrates the cost savings too. By swapping those massive raw files out for statistical summaries, they achieved a whopping 97x token reduction for enterprise data. So instead of spending 48,000 tokens, which, costs real dollars at scale, the prompt drops down to just 500 tokens. That's literally fractions of a cent per generation.
But as with all great research, we definitely have to be fair about the limitations. There is a catch here. If your underlying data structure radically changes, something called schema drift, well, the zero-token refresh fails, and you do have to regenerate the whole thing. Also, at least for now, identifying exactly what rules belong in those 4 memory categories requires a human to manually design the system and set up those constraints. It doesn't just magically sort itself automatically yet.
Finally, Section 6, Impact and Key Takeaways.
So here is what you should really take away from this explainer. First, this framework completely solves that frustrating stateless AI amnesia. Second, it does it by strictly curating memory into those 4 specific categories while actively throwing away the distracting session history. Third, it enables those amazing zero-token updates for recurring tasks. And finally, because of all this, it drastically cuts enterprise computing costs and user time. It's a huge deal because it proves that smart context management is arguably the most powerful lever we have for AI efficiency right now.
Which leaves us with a final, really provocative question to think about. Is context management, rather than just waiting for bigger, raw model capability, the true secret to unlocking autonomous AI? As this paper clearly shows, the future of AI development might actually rely far more heavily on what we deliberately choose to remember and, crucially, what we intentionally choose to forget. Thank you so much for joining me on this explainer, and I'll catch you in the next one.